यार 23 का है।
जी हेलो अस्सलाम वालेकुम।
वालेकुम सलाम सर।
Okay, let me
वालेकुम सलाम सर।
hello. Let me mark your attendance. Asma Bibi,
Present, sir.
Awais Ahmed,
प्रेजेंट सर।
Aisha Liaquat, Dilawes,
Present, sir.
Ijazul Haq, Ijazul Haq, Parwa Zafar,
Present, sir.
Ghulam Murtaza,
प्रेजेंट सर।
Maryam Manzoor,
Present, sir.
Muhammad Ahmed Fareed,
प्रेजेंट सर।
Muhammad Fayaz,
यस सर।
Muhammad Zahir,
प्रेजेंट सर।
Muhammad Amirul Azim, Nageen Fatima, Nimra Khalil, Noor Rahman,
Bakri, sir. Present, sir.
Noor Rahman,
प्रेजेंट सर।
Nurulan,
Present, sir.
प्रेजेंट सर। प्रेजेंट सर।
okay, Noreen Kausar,
Yes, sir.
Noshin Nisar,
Present, sir.
Ramizul Hassan,
Present, sir.
Samiullah,
प्रेजेंट सर।
Sumaya Lal,
Present, sir.
Sayyida Arij, Umama Shehzadi, Umar Farooq,
प्रेजेंट सर।
Usama Habib,
प्रेजेंट सर।
Usman Tariq,
प्रेजेंट सर।
Zulekha Aftab,
Sir, Eman. Sir, Eman Gul.
okay, let me recall the names of
मिस निजी को नहीं।
absentees. Yeah, Zulekha Aftab, Umama Shehzadi, Sayyida
Present, sir.
Arij, कौन?
Umama.
Okay, Sayyida Arij, Nimra Khalil,
सर
Nageen
जुलेखा
Fatima,
आफ्ताब भी प्रेजेंट है।
Zulekha Aftab भी present है. Okay, Nimra Khalil, Nageen Fatima, Muhammad Amirul Azim,
Sir, present, sir. Nimra Khalil, present, sir.
Ijazul Haq, Aisha Liaquat, okay, जी अनम रियाज,
Present, sir.
सादिया फारूक,
Present, sir.
जी निमरा खलील, Hello,
Yes,
Nimra
sir.
Khalil ji, you have raised your hand. Okay. Okay. Last time we started a topic that was completeness. So let me recall what uh, do we mean by completeness of metric space. Completeness of metric space. Any one of you? G.
Sir, a Cauchy sequence converges in any
Yes.
space.
Okay. Metric space XT. Metric space XT is complete if every Cauchy sequence converges. So we know what Cauchy sequence is. Now we will discuss some examples of complete metric spaces. Last time we discussed that example. I gave you the homework to show that R is complete with usual metric. So in real analysis one, we proved that R is complete. So now we will show that Rn is complete with metric. So D is the metric defined on Rn. So we will show that this Rn is complete with this metric. Just like R is complete with Euclidean metric, we can show that Rn is complete with this Euclidean metric. R is not complete with every metric. If you change the metric, the same space, I mean, it is not no more the same space if you change the metric. R might not be complete with respect to every metric on R. So there are metrics on R so that R is incomplete. We will discuss some questions in today's class. So I will discuss those metrics. when R is incomplete. But with the Euclidean metric, R, Rn are complete matrix spaces. So to show that a space is complete, we need to consider an arbitrary Cauchy sequence. Then we will show that, then we will construct an element to which arbitrary Cauchy sequence converge. We also need to show that the element we will construct belong to the space. So that will complete our claim that Rn is the given space is complete with the given metric. So let's assume a Cauchy sequence. So we can write the proof actually. So more or less the same technique will be used in proving other spaces are complete, like LP spaces, L infinity, C0, CAB. So I will discuss the proof for Rn and maybe one more space. The rest I will leave for you to read and complete. Okay. So let Xm be a Cauchy sequence in R. N. Let Xm be a Cauchy sequence in Rn. So every element in Rn is the n tuple. So every element in this sequence is also n tuple. So let me given as Xm is equal to xi 1 m, xi 2 m, up to so on xi n m. So this sequence actually, so first term of the sequence is x1, which is equal to xi 1 1, xi 2 1, xi 3 1, up to so on xi n 1. Similarly, the second is xi 1 2, xi 2 2, xi 3 2, xi n 2, up to so on. So each element is n tuple in Rn. So if you consider a Cauchy sequence, every element of the sequence is n tuple. So we need superscript as well. Subscript is used to show the tuples, first tuple, second, third, up to so on. The first coordinate, second coordinate, third. Each element has n coordinates, n arguments. So we need another script to show the number of term in the sequence, Cauchy sequence. So that will be the representation of the Cauchy sequence in Rn. Okay, as Xm is Cauchy, so for every given epsilon, there is a natural number n such that such that dx m xn is less than epsilon for all mn greater or equal to n. That is the definition of Cauchy sequence. That is, so what is the metric on Rn? Euclidean metric I from 1 to n. So maybe we should use some other subscript here because we are considering n for Rn. So here we can use k maybe. So I from 1 to n xi I m minus xi I k square root. That is the metric. That is the distance between xm and xk. It is less than epsilon. So this implies summation I from 1 to n xi I m minus xi I k absolute value square is less than epsilon square. Square function is increasing function, right? So we can square on both sides to get the last inequality. And this hold for all mk greater or equal to n. This hold for all mk greater or equal to n. So this further implies, tell me why I will write this xi I m minus xi I k less than epsilon square for all m k greater or equal to n and for fixed I where I is greater or equal to 1 lesser or equal to n.
Because all the modulus value are positive because they have a square. So if you select one, so it will be less than the summation of all the values. From I
Yes,
to
thank
I
you.
is 1 to n.
Yes, because summation is less than epsilon square, and this is the sum of non-negative numbers. So sum of non-negative numbers is less than epsilon square. Then all those numbers are less than epsilon square. If the sum is less than epsilon square, well, that is true for non-negative numbers only, not for all the numbers. So for any I, it will be less than epsilon square because the sum from I equal to 1 to n is less than epsilon square for every fixed I, whatever I you fix. Maybe you fix I equal to 1, I equal to 2, I equal to 3, I equal to n. So for that I, it will be less than epsilon square, and that is a square. So the square root function is also increasing function. This imply that xi I m minus xi I k mod square less than epsilon square root for all mk greater or equal to n and for fixed I greater or equal to 1 lesser equal to n, and I is a natural number, right? So this implies xi I m minus xi I k mod is less than epsilon for all mn greater or equal to n for fixed and for fixed I.
This completes the proof, sir.
So fixed I, what is this? This is a
R.
exi
So this
I
is,
m
so
exi
this is R
I.
space. R space.
Yes. So if you have fixed I, for example, maybe I equal to 3. So that mean I equal to 3, then exi 3 1, exi 3 2, exi 3 3 up to so on. It is a sequence of real numbers, right? Exi I m is a sequence of real number if you fix I. So that is the ith tuple. So in the Cauchy sequence, if you consider ith tuple only, so that will be the sequence of real numbers. So if a sequence of I is fixed here, so you can just consider this as am minus a k mod less than epsilon. So for any epsilon, there exists this natural number such that we have, we have this one. So that means so this implies for fixed I greater equal to 1 lesser equal to n, xi I m is a Cauchy sequence of real number. Cauchy sequence of reals. As R is complete, so xi I m converges to some element in R, to some real number. So we have fixed I. So for each fixed I, xi m is a Cauchy sequence of real numbers, so it converges to some real number. So call this number real number xi I. Say xi I. That is xi I m converges to xi I for fixed I, where I is greater equal to 1 lesser equal to n, and I is an integer. So this hold for each I, no? So I was fixed, but the same, we can do the same thing for each I. So we didn't specify I is 1, 2, 3, 4. So you can do this for each I from 1 to n. So now consider an element. So we can define an element x, which is equal to xi1, xi2, up to xi n, because this xi I exists for each I from 1 to n, for each integer from 1 to n. So we have this number, and this belongs to Rn. By definition, it belongs to Rn. Rn is a set of n tuples, so it belongs to Rn. So further, if you consider this, so if you consider this inequality, call it 1. So if you let the limit n approaches to infinity in k approaches to infinity, sorry, in this inequality, so what will you get? So letting k approaches to infinite in 1. So that means limit n approaches, sorry, k approaches to infinite, summation I from 1 to n, xi I m minus xi I k square root less than limit k approaches to infinite, but there is no limit on that side, it's fine. So that will be less or equal, right? So this implies summation k approaches to infinite, sorry, I from 1 to n, xi I m. We know that xi I m converges to xi I. So xi I k converges to xi I less or equal to epsilon. And this hold for all m k greater equal to n, and this hold for all m greater equal to n. So what is this? That is the distance between x m and x we have defined less than epsilon for all m greater equal to n. So this implies that xm converges to x belong to Rn. So this implies that Rn is complete. Okay, so any question, comment?
No, sir.
So we have the definition of, so this, if for any given epsilon there is n such that dxm x less or equal to epsilon, that means xm converges to x. This is the definition of convergence. But in the definition we use the strict inequality. But here we are using less or equal. In the limiting process, we had in one the strict inequality here, but in the limiting process, the strict inequality is usually turned into less or equal. So like we have 1 over n is a sequence of real numbers greater than 0. But when you consider the limit 1 over n, that is greater or equal to 0, limit n approaches to infinity. So we can get rid of this less or equal. We can have strict inequality. Maybe you can use from the start, instead of epsilon, you can use epsilon over 2. So that will be epsilon over 4, epsilon over 4, epsilon over 2, epsilon over 2, right? And this is less than epsilon. And then we have epsilon over 2 here. So epsilon over 2, epsilon over 2, and epsilon over 2 is less than, strictly less than epsilon, because epsilon is a positive number. So xm converges to
Yes,
x. Okay. So let me discuss. Okay, similarly, you can prove L infinity sequence of space of bounded sequences with metric dxy is equal to the supremum of xi I minus eta I belong to the natural number is complete. Example number 3. So let me know if you, when you read it, and if you do not understand its proof, you can, so we can discuss. So example number 4, LP with metric. LP is a space of sequences of real numbers or complex numbers. So X is a sequence that belong to LP if summation xi p I from 1 to infinite, it is this series converge. So this LP is complete with the metric dxy equal to summation I from 1 to infinite xi I minus eta I p 1 over p. Where x is this sequence xi I and y is this sequence eta I. So you can read the proof from the book or anywhere you would like. So you can do that. So let me discuss some questions. So for example, question number 1. So that is on page number 39. So I'll come back to the complete or incomplete spaces after discussing some questions. So question number 1, let AB belong to R and A is less than B. Show that the interval AB is an incomplete subspace of R. So in this book, they are using the capital R for, so this capital means when they, capital means the set of real numbers with the Euclidean metric. So they do not write it, but when they write this way, that means the metric is the usual metric. So any idea to, from your side, how to show that this is incomplete? I mean,
सर कैन आई
yes, please.
सर पहले इसको सबस्पेस प्रूव करेंगे और उसके बाद
Mhm.
एक ऐसा सीक्वेंस ले लेंगे जो इस इंटरवल में कन्वर्ट मतलब कि वैसे बेशक कन्वर्ट करता हो लेकिन इस इंटरवल ए बी में कन्वर्ट ना करे देन हम कहेंगे कि कंप्लीट ये इनकम्प्लीट है
Yes. So, yeah, that is right answer. So complete. First, we will prove that this is a subspace of R. So in metric space, how do we define a subspace? So if xt is a metric and y is a subset of x, and if we restrict the same d on y, we call it d tilde, and d tilde when restricted on y is same as d on x. So d tilde d is same, right? So we use the same metric for y. D tilde is actually the restriction of d on y, the same distance function. That is a subspace. So it is subspace, interval AB is subspace. And then the next, at the next step, you can consider, because a space is complete if every Cauchy sequence converges. So if you can find a Cauchy sequence which does not converge, that means the space cannot be complete, it is incomplete. So find a Cauchy sequence which converges, which does not converge in AB. So Cauchy sequence which does not converge in, you need to consider a sequence in this subspace AB, interval AB. Sequence in the interval AB which is Cauchy but does not converge. So you can maybe if you consider a sequence Xn, so let Xn be defined as A plus 1 over n. But if I consider A plus 1 over n, maybe it goes outside this interval. So how can I be sure that the sequence stays in this interval? So A plus, so what is the length of this interval? B minus A, right? So if you add B minus A divided by n, so you can check that the sequence belongs to this interval AB. Or maybe you can prove it as a very small exercise that this belongs to this interval AB. So A plus B minus A over n is a sequence. And this sequence, so first step you need to show that. So claim Xn is Cauchy. So prove these claims, right? So Xn belong to AB. Let me write the claims. So number one claim is Xn belong to AB. Number two claim is Xn is Cauchy. Number three claim is Xn converges to A as n approaches to infinite. Number four, AB is incomplete subspace. So you can consider the limit n approach to infinite and 1 over n goes to 0, so Xn goes to A as n approaches to infinity. But I want you to prove it using epsilon delta definition. Xn is Cauchy and Xn converges to A. And as A does not belong to the interval AB, so AB is incomplete metric space. So do this question, these parts as an exercise. So if you will have any problem, you can ask me. So question number two is very similar to what we did in proving that Rn is complete. In question number two, the space is Rn, space of all ordered n tuple, but metric has been changed. Txy is the metric, maximum metric. Xi I minus eta I is an integer greater or equal to 1, lesser or equal to 1. So Rn is complete with this metric. You can easily prove. And there was another metric, D. So what was this metric? So there was another metric. So that was D infinite metric, right? D1 metric. So where summation I from 1 to n, what was xi I minus eta I mod. So prove that these metrics, Rn is complete with these metrics as an exercise. On the very similar lines to the proof of Rn is complete with the Euclidean metric.
Sir, in question 2, there is a restriction on y equals to only eta j, not I.
Y is equal to eta.
Y is equal to eta j. And
Eta
d
j.
of xy equals to max max of और नीचे जो है वो restriction है j and xi j minus eta j. So it's confusion.
Let me check on the book. But it doesn't matter, the subscript can be anything. So you can use
Yes, the subscript doesn't matter, but x equals to eta 1 to eta n, and sorry, xi 1 to xi n, and y equals to only eta j. So it causes confusion.
okay.
J is equal to
सर ये
1 from n.
स्पेस बन जाएगी ना Rn की, अगर y को हम फिक्स कर रहे हैं ईटा j पे तो वो सब स्पेस है Rn की.
J is equal to 1 from n.
So did you get her point? So she's saying okay, when they defined metric dxy equal to actually they are using here j, the maximum xi j minus eta j, right? So where they already defined what is x. X is this sequence xi1 xi n, right? And then they wrote where y is equal to eta j, right? So she's saying that y is equal to eta j, it's only one tuple, while x is n tuple, but it is just matter of notation. They do not mean it one tuple, so we use the notation. Even we have been using the notation for the sequence xi. You can say that I from 1 to up to n somewhere.
Right.
So it is j from 1 to n. So let me discuss some more questions. Question number 3. is something, let M is a subspace consisting of all the sequences X, xi I, or xij with at most finitely many zeros, with at most finitely many non-zero. Find a Cauchy sequence in M which does not converge. Converge in M. So that will prove that M is not complete. Yes. Any suggestion for such sequence? So sequence with finitely many non-zero terms. So consider this sequence. Xi I n, that is xi I 1, sorry, n, that is 1, 1 by 2 up to 1 over n, 0, 0 up to so on 0, 0. Right? So this is a sequence. The first term with x1 equal to, that is 1, 0, 0 up to so on. That is the first term of the sequence. Second term will be 1, 1 by 2, 0, 0, 0, and x3 with 1, 1 by 2, 1 by 3 up to so on, up to so on. Xn is equal to 1, 1 by 2, 1 by 3 up to so on, and xm is equal to 1, 1 by 2 up to 1 over m, and then we have 0, 0 everywhere. So that is a sequence. So xn converges to, it is a sequence, it is, xn is a sequence in L infinity, because every term of the sequence is bounded sequence. It is bounded sequence, bounded. Right? So you can check that easily. Xn converges to x as n approaches to infinity, where x is equal to 1, 1 by 2, 1 by 3 up to so on. And this x does not belong to M. It belongs to L infinities. It is a bounded sequence. It is 1 over n sequence. It is bounded. But in M, we are considering those sequences with finitely many non-zero terms. But this does not have this has infinitely many non-zero terms. So we have a sequence which converges to something which does not belong to M. So we want to show that Xn is Cauchy sequence. So if Xn is a Cauchy sequence, so this is a Cauchy sequence in M which does not converge. So M is incomplete. Okay. Now, this part I'm leaving it for you to show. This shouldn't be difficult for you. Show that Xn converges to X. So the metric on L infinity is the supremum metric, right? So you can consider this X 1, 1 by 2, 1 by 3 up to 1 over n, right? The distance between Xn and X. So up to 1 over n, that will be 0, but you are considering the distance which is the supremum distance. So that will be 1 over n plus 1, the distance, and that approaches to 0. The distance between Xn and X will be 1 over n plus 1, and that converges to 0. So Xn converges to X. So just write it. So now we want to show that Xn is Cauchy. So fix n m greater than n, right? And consider this distance between xm and xn. So that will be equal to supremum I from n to what is xn? Xi I m minus xi I n. That is equal to supremum I from 1 to n. So remember xm is this sequence, right? M is bigger than n. So m is greater than n, and 1 over m is less than 1 over n. So we have 1 by 2 up to 1 over m, and we have 1 by 2 1 over m, 1 over n, sorry, m plus 1 up to that will be 1 over n, and 0 0 0, and here we have 0 0 0. So that is the sequence xi I m, xi I n. So this distance is actually so you subtract the corresponding coordinates terms in the sequence and consider the absolute value. So 1 minus 1 0, 1 by 2 minus 1 by 2 0, 1 over n minus 1 over m is 0. So we have only non-zero terms starting from here. 1 over n plus 1, then 1 over n plus 2, then 1 over up to so on. So the supremum will be just equal to 1 over n plus 1. And this goes to 0 as mn approaches to infinity. So this implies that limit mn approaches to infinite 1 over, sorry, dxm xm is equal to 0. So this implies that xm is Cauchy sequence.
सर 1/m+1 नहीं आएगा
1 over
m+1
कैसे?
सर क्योंकि हमारे पास टर्म्स तो सिर्फ 1/1 + m+1 की
Oh.
आगे वाली नहीं बचेगी जब सब्ट्रैक्ट करेंगे
That term is 1 over n plus 1.
ओके सर
Okay. Okay, all right. So 1 over m plus 1, yes. M plus 2, 1 over m plus 2 will be less than 1 over m plus 1 and up to so on. Yes, 1 over m plus 1. Thank you. So xm is Cauchy sequence which does not converge. So there is question number 4. Show that m in problem 3 is not complete by applying theorem 1.4.7. That theorem says that if you have a sequence in the space which converges to something which is not in the space, so that space is not closed. So a subspace is complete if and only if it is a closed subset of the metric space. Since M is not closed, so it is not complete subspace by theorem 1.4.7. So question number 5. So I assume you have the book in front of you. So like show that the set of all integers with metric D defined by dmn is equal to m minus n is complete metric space. So set of integers with the usual metric, Euclidean metric on R, same metric. So it is complete metric space. So what kind of sequences, if you consider any Cauchy sequence or Cauchy sequence of integers, so what kind of Cauchy sequence, what kind of sequences are Cauchy sequences in this space? Constant sequence, yes, because so whatever sequence you will consider in this space, that will consist of integers. The smallest distance between two integers is 1. So if you consider the epsilon less than 1, then the distance can be less than epsilon if after some stage the sequence becomes constant. So not the constant sequence, the sequences which are eventually constant are the sequences which are Cauchy sequences. Eventually mean after some time. So maybe this sequence is also a Cauchy sequence. 1, 2, 3, 4, 4, 4. So this sequence Is it a constant sequence? No, it is eventually constant sequence. So constant sequences converge to the constant. For example, this sequence converge to 4. So this space is complete. So you can just write the solution. Question number 6 is a very important question. Like, so space is R with metric dxy equal to 10 arc10 x minus arc10 y. Remember, this is a metric. If you consider this function f of x minus f of y, where f of x is equal to tan inverse x. So that metric which we defined with the help of a function f, the metric we called it transfer across metric. So this is incomplete. I mean, R is incomplete with this metric. With the Euclidean metric, it is complete. So this function is called transfer across function f of x equal to tan inverse x. So you can move from complete metric space to incomplete metric space. Absolute value metric. So this is actually the composition of well, you can write it as d fx fy, right? Where not d, p, where p is this metric x minus a Euclidean metric. So p is the Euclidean metric, and then p fx fy, it is a metric if f is 1 to 1, and this function is 1 to 1 function, tan inverse x. So prove that this is incomplete. Metric space.
सर
Yes.
सर ये जो tan इनवर्स आपने ये दिया इसमें इनइक्वालिटी, तो नहीं इक्विलिटी सर, ये ऑल ट्रिग्नोमेट्रिक फंक्शंस के लिए होल्ड करेगी या सिर्फ tan के लिए ही करेगी? जैसे हम साइन इनवर्स या कोस इनवर्स ले लें.
Okay. So any of you would like to answer her? जी.
सर अगर यहाँ पे x अप्रोचेस टू इन्फिनिटी होगा तो इसका जो आंसर आएगा वो π/2 आएगा. सर तो दोनों साइड पे ये π/2 पे ये कन्वर्ज करेगा. ये arc10 tan inverse x.
अच्छा. नहीं, she asked a question that we are using tan inverse x. So what happens if we use some other trigonometric function, cos inverse x, sin inverse x, or something like that?
सर साइन इनवर्स कोस इनवर्स फंक्शन 1 to 1 नहीं होंगे, तो वो 1 1 वाली कंडीशन को सेटिस्फाई नहीं करेंगे.
Yes, very good answer.
सर मीन सिर्फ वही हम लोग लेंगे जो 1 1 होंगे.
ये किसने आंसर किया था पहले?
सर मैंने अनम रियाज.
जी अनम. हाँ, तो ये हम पहले थोड़ा सा डिस्कस कर चुके हैं कि मतलब D is a metric, P is a metric, and F is a function. P is a metric on X. F is a function from X to X. So P F X F Y. P is a metric. It is given that P is metric and F is this function. Then D is metric only if F is 1, 1. So otherwise it is pseudometric actually. So it is not metric, pseudometric. एक तो आंसर ये है, तो दूसरा आंसर ये है कि so let me try to answer differently. So I forgot the graph of tan inverse X. Maybe it looks like this one. Tell me if I'm wrong. Right? So that is a graph of tan inverse X. So it is asymptotic to this line pi by 2 and minus pi by 2. So tan inverse X is defined for all real numbers. So if you look at this function, tangent inverse function, it takes R onto what? Minus pi by 2 to pi by 2. So it maps R onto open interval. And then you apply this absolute value metric. So with absolute value metric, that open interval is incomplete. So एक तो यहाँ से आपको आइडिया हो जाएगा, ठीक है, मतलब you can think of restricting other trigonometric functions, कुछ और questions बनाए जा सकते हैं, but यहाँ पे आपने इस पता नहीं do you get my point or not? So tan inverse takes maps R onto this, and you know that this is incomplete on with Euclidean metric. So that is why it is incomplete. I mean, we will prove it is incomplete, but just to see why it is incomplete. So it is a metric on R. So इसी से related मैं एक question और लिखता हूँ जो बाद में हम देखेंगे. Question number 7. Consider x equal to R and define metric dxy as tan x minus tan y, नहीं R नहीं, minus pi by 2 to pi by 2. So what is the graph of tan x from so tan is defined, tan is 1 to 1 only in this interval, no? Minus pi by 2 to pi by 2. Now this function tan takes this interval minus pi by 2 to pi by 2 and map it onto R, and R is complete with Euclidean metric, absolute value metric, and this x with D is complete metric space. Remember, this interval, open interval, is incomplete with Euclidean metric, but if you use this transfer across function tan, then it is complete. This open interval in R is complete metric space with this metric. With usual metric it is not. So why it is transferred into complete? So it maps the open interval into the whole real line. So it maps minus pi by 2 to R, and R is complete with the Euclidean metric. So in that sense, you or code main. So that will give you idea whether the space is complete or incomplete. But you need to use the one-to-one function. So if the function is not one-to-one, 10 tangent function is also not one-to-one. So you can restrict it to the domain where it is one-to-one. And then you can think of other spaces, whether complete or incomplete. Hello?
Yes, sir, got it.
Okay. So let's have a break for maybe how much time?
20 minutes.
Okay, 20 minutes. All right. So I'll see you after 20 minutes. Hello?
Assalamualaikum, sir.
Walaikum salam. So, can you hear me? All of you?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes,
Sir,
yes, sir.
I have. Excuse me, sir.
Yes, yes.
This is Samuel. I have a suggestion, sir. In every theorem is have two or three or more than this question is solved. Is all of my classmates to completely know in this matter? Okay. Please solve the two or three more than this question.
Sorry, say again.
Hello, sir.
Sorry. Yes. Can you please say it again?
And this subject is so okay. Yes, sir. Okay. This is Samuel, and I want to be learning this subject is about every theorem, two, three, and more than this, questions solved, and all of my classmates completely understanding this subject in this matter.
Hello? Ji Samira, I mean, there is a problem. I
Yes,
couldn't
yes.
properly the question.
सर चैट का ऑप्शन ओपन कर दो चैट में मैसेज लिख लें समझ आता है
Ah, yes. Chat option is open already. ये कहाँ से open करते हैं chat option?
मीटिंग सेटिंग में से होगा और में chat में।
Open. I don't know.
Yes, sir, this is internet is so slow, and I am in Afghanistan, Jalalabad city. I want to be in this matter. Every theorem have four or three more than this question solved, and every theorem is I have. I don't have in this problem. Okay, sir.
Okay. So you do not have any problem.
No,
So
I
you
don't have
understand.
problem with this lecture, but
Okay.
every
So
theorem is okay. Yes.
you understand
Yes. Yes.
whatever we have
Inshallah.
discussed so far. Ah, okay. That's good. So what we were talking about, that this space is incomplete. So to show that the space is incomplete, you can consider you should have at least one Cauchy sequence which does not converge, right? So consider this sequence. So claim, there are two claims that Xn is Cauchy Number 2. Xn doesn't converge. So let me show Xn is Cauchy. Consider dxm xn, which is equal to tan inverse m minus tan inverse n. So that can be written as tan inverse so we can add,
Sir?
subtract. Yes.
Sir, this is a solution of a question number 6 or a question number 7?
I don't know. Question number 6.
Okay, sir.
Tan inverse pi over 2. So we can add, subtract pi over 2 and just write. So this approaches to 0 as m approaches to infinite and n approaches to infinite. So this implies Xn is Cauchy sequence. So this tangent function is the graph of the tangent function is this one. So if x approaches to infinite, tan inverse x approaches to pi over 2 and tan so when x approaches to infinite, tan inverse x approaches to pi over 2. So tan inverse m approaches to pi over 2, tan inverse n approaches. So it approaches to 0 as m approaches to infinite. So Xn is Cauchy sequence. Does not converge. If Xn converges to X, some X belong to R, then dxn X converges to 0 as n approaches to infinite. That is, limit n approaches to infinite, tan inverse Xn minus tan inverse X equal to 0. This implies that limit n approaches to infinite, tan inverse n minus tan inverse X equal to 0. So n approaches to infinite, tan inverse n approaches to pi over 2. So that means this implies that pi over 2 minus tan inverse x is equal to 0. This implies that tan inverse x equal to pi over 2. So this implies that tan pi over 2 is equal to x. But this is contradiction actually. But tan inverse x is not equal to pi over 2 for all x belong to R. So hence this sequence does not converge.
सर दूसरी बात है 10 पाई बाय 2 is equal to x है तो x is equal to infinity हो जाएगा तो as infinity does not belong to R.
Oh, sorry. Yeah. Tan pi over 2 is equal to what?
Infinite number, infinity.
10 pi over 2, I mean 10 pi over 2 is not well defined. Yeah, 10 is not defined at pi over 2. 10 is, I think I shouldn't write this. So 10 pi over 2 is not equal to infinity. It is not defined at pi over 2 unless we define it. So we make it, we extend it in some sense, but we are not going to extend this function on the extended real. So 10 inverse x is not equal to pi over 2 for all x. So that completes the proof. So the second part, so show that is your homework. So I will give you one assignment, and maybe I will give you one assignment and one quiz in the next week. So quiz will be from chapter number 1, and assignment will not be from this book. So I will give you some questions from somewhere else. So you need to solve those questions. I will upload on LMS. I will let you know via email as well. So solve this question number 7, right? Show that this is complete. So you can consider an arbitrary Cauchy sequence and show that Cauchy sequence converge. So that is your homework. Maybe so make it a quiz number 1, right?
Yes, sir.
So let me create a quiz on LMS. But there are 2 courses. Okay.
सर इसका सॉल्यूशन आपको ईमेल करना है या एलएमएस पे अपलोड करना है हमने?
I think you can send me via email the solution.
सर कब तक
कब तक? Oh, I think you need to upload on LMS. So I will just take some time out after the class, and I will create folder on LMS. Let me do it
Sir,
right
when
now.
will you conduct this?
So I will not conduct it. I will give you maybe 3
Okay,
to 4
sir.
hours. So maybe you can upload it by 12 p.m. So you will have 3-4 hours, or maybe I can give you time.
Sir, on which date?
Right now. So let me create a folder.
Yes, sir. आप अभी create कर लो.
Yes.
सर क्विज नेक्स्ट लेक्चर में होगा कि
Sir, it's a surprise quiz.
क्विज अभी हो रहा है आपका, ठीक है? So
सर अभी तो नेक्स्ट
क्या
में करने
नेक्स्ट तो नहीं कर सकते. हाँ, I can give you some time. मतलब usually you only need 20 minutes for this quiz, but I will allow you to submit the quiz by tomorrow morning.
Okay, sir.
So you can write the question. So I will not upload any file. So you can write the question. Question is on the screen. So write the question on your page and solve it and upload as one PDF file, and name your PDF file with your first name followed by your student ID. So quiz number 1. So there is no file. 29. So that will be available 20, 30, 40. And that is due tomorrow. 30. 8 a.m. 9 a.m. maybe. 10 a.m.
Quiz is next week, teacher.
Sorry?
Quiz is next lecture.
No, quiz is right now.
Quiz right now.
Yes. But you can upload
Quiz
your
num-
solution by tomorrow morning.
सर जी अभी क्विज हो रहा है?
Yes.
अच्छा सर जी, मेरी तो फर्स्ट क्लास है सर जी। ये ना बाद में एडमिशन हुआ था मेरा सर जी, तो मुझे इसकी समझ ही नहीं आ रही थी सर जी, मैं कैसे दूं फिर?
Sir ji,
मेरे पास सर
my AMS
Why-
doesn't work.
Why is it your first class? I mean, can you explain?
सर जी मेरा ना बाद में एडमिशन हुआ था, एक और मेरा क्लास फेलो था, उसका वीकेंड पे हुआ था, मेरा रेगुलर में सर जी। तो इसी वजह से ना सर जी बाद में एडमिशन हुआ था, तो इसी वजह से ये क्लास बाद में ली है सर जी।
So, chale, you can do something. So you have time. So you got, I mean, 8 to 10, 14 hours. So things can.
अच्छा, ये क्वेश्चन नंबर सर जी क्वेश्चन नंबर 7 को करना है?
क्वेश्चन नंबर 7 को करना।
ठीक है सर जी, फिर मैं इंशाल्लाह करके सेंड कर दूंगा सर जी।
बुक से भी स्टेटमेंट देख सकते हैं?
बुक में है स्टेटमेंट इस क्वेश्चन की? लेट मी चेक। बुक में है ये क्वेश्चन?
तो ये -5/2 है या π/2?
5/2. So बुक से स्टेटमेंट देख सकते हैं, but I don't see this question in the book here.
No, sir. Question number 6 is different. We have to prove incomplete metric space in question 6, but you gave x
You need
equal
to-
to -5.
Yes, you need to do question number 7, not 6. 6 I just solved
Yeah.
it.
Yes, sir.
From book?
From book. This question is not from
Teacher,
book, but it's not difficult. You can do it. You can try. You have time to try.
Okay, sir. Okay.
So I did some mistake, maybe 30th March. Yes. Yes. Yes, Samir. So the folder has been created. So you can solve it and you can upload. So where you will upload?
सर ये समझ नहीं आई, दोबारा से बता दें। 5/2 है या π/2 है?
5/2.
जी
Okay, जी π/2. Pi. So you need to actually
Questions.
نورحمان كزما غاوري جرانا
So
تغاور
you have, so you have
نورحمان
13 hours and 17 minutes to do that quiz.
Quiz next next Monday or right now?
نو رحمان که زما غږ اوري زه به دې پوه کړم دا اووم نمبر سوال چې دی همدغه ستاسو کویز دی همدغه کویز همدغه حل کا
So let me so do you see the folder? So you can upload your solution in quiz number 1 folder. So I have created so this is pi over 2. This is pi over 2. And metric is D. And pi. You need to show that this metric is complete. Okay. So I intend to discuss some more questions from the previous exercises, but I'm afraid I do not have much time today. Where is everyone? Hello?
Yes, sir.
So this lecture ends.
Okay, sir.
Yes. Okay, sir.
Thank you, sir.
Okay, sir. Thank you.
Okay, sir. Thank you.
So you need to upload your solution 10 a.m. tomorrow. By 10 a.m.
Yes, sir.
tomorrow.
Okay, sir.
Sure, sir.
So there are some more questions like for example, one question, show that a discrete metric is complete. So for a non-empty set, we define distance as dxy equal to 0, 1, if x equal to y, if x not equal to y. So this metric is complete. So you can consider any Cauchy sequence in it. And the Cauchy sequences in discrete matrix are the sequences which are eventually Cauchy sequences. With the same reason we used for the metric on the set of integers, because the distance between any two number is either 0 or 1. So if you consider any epsilon greater than 0, which is between 0 and 1, less than 1, or so then the distance between two numbers can be less than epsilon, which is less than 1, if the distance is 0. Distance is 0, then the terms have to be equal. So the eventually constant sequences are Cauchy, and those sequences converge. So this discrete metric is complete. So then there is very important space CAB, space of continuous functions defined on this interval AB. So we have two types of metric we considered so far on CAB. So that is maximum metric. So maximum xt minus yt, and t maximum taken over t belong to the interval AB. So CAB with this metric is complete. But if you consider this metric d2xy, that is the integral from a to b xt minus yt, absolute value of dt. With this metric, it is not complete.
Teachers,
Yes, yes.
Assalamu alaikum.
Hello, yes.
What was the first question? I didn't know it's problem in network.
Sorry, say again.
What was the first question?
What was the first question?
I didn't know by this question what was the first question. It's problem in network. Okay.
Uh, Sorry, say again. You mean question? So that is not first question. That is, sorry, question number 10 from the book.
This is
So it is question number 10.
show
that discrete metric space is complete. So this space D2, if you consider this sequence, X and T. So consider this space C minus 1 to 1, right? So X and T is defined as 0. So when T is greater equal to minus 1, lesser equal to 0, and NT when T is greater than 0, less than 1 over n, and T is greater equal to 1 over n, 1. That is equal to 1. So we can draw the picture of some terms, right? So from minus 1 to 0, it is 0. And 0 to 1 over n, it is equal to nt. And then from 1 over n to onward, it is equal to 1. It's constant again. So this sequence is actually Cauchy sequence, but it converges to some function. So if you look at this function, 1 over n goes to 0 as n approaches to infinite. So xn t converges to this function xt, which is equal to 0, which is equal to 1, and 0 whenever x belongs to minus 1 to 0, and when x is greater than 0, less than 1, it is equal to 1. And x, this function xt is discontinuous function. X does not belong to CAB, C minus 1 to 1. This function does not belong to this. But this sequence xn is a Cauchy sequence. So and you can show that this sequence is Cauchy sequence. This is not exactly the sequence being used in the book. So in the book you will find a different sequence, but very similar to this one. So you can read read it and answer this question number maybe answer question number 13 as well. So after reading this proof that it is not complete meter space. So after reading that xm is a Cauchy sequence, but it does not converge. It converges to something which is not in the space. Okay. So then the next is there is the next section 1.6 that is about completion of a metric space. So I'm giving you the reading of assignment for this section. So there can be a YY exam from this section. Reading
Complete
assignment.
proof.
Sorry,
Complete proof of the theorem.
say again.
So there is a theorem of 4 pages, 5 pages length. So the complete
Yes.
proof of that theorem.
Yes, complete proof, everything, maybe the exercise as well, the questions in the exercise as well. So reading assignment. So maybe MS students, for MS students, this Viva exam, so this exam might not be the similar for MS students, but for PhD student, certainly there are some marks for that. Or
Yes, sir. सर ये कब होगा वाइवा?
yeah, it can happen maybe after 2-3 weeks.
Okay, sir.
Sir, this is not for the MS students.
This is for the MS. Reading assignment is for the MS student, but the marks can vary.
All right,
The
sir.
absolute marks for MS student.
Only
might
the
be-
reading mean what it means, sir?
It means I don't know. Maybe I will explain the next time.
Sorry, but
For a serious response from the
okay,
PhD
right.
students, more serious response. I mean, so they should work more on this reading assignment. So maybe I will ask some PhD student to present whatever they have prepared.
Okay, sir. All right.
Maybe.
Thank you, sir.
So what is the completion? Not every metric space is complete. We have seen many examples of metric spaces which are not complete. But every metric xt might not be complete. So this space xt might not be complete. But there exists for every metric space another metric, right? So which is complete. So there exists another metric which is complete, and in that complete metric space there lies a subspace which is isometric to this space xt, and this subspace is dense in the complete metric space. So every metric space has a completion. That means every metric space has some other metric space which is complete, and the metric space is dense in the metric space. So is dense with respect to some mapping. That mapping is called
Excuse me, sir.
the mapping that preserve the distance. So isometry mean if you consider distance in one space between two elements, the mapping is isometry if the distance between the images is same as well. So just read it. So every metric space has a completion. So there is a complete metric space in which the metric space is embedded. That is the completion theory. So maybe the next class, although I have already talked to Professor D'Souza to teach next class on Monday. So he will deliver a lecture on some topics in functional analysis.
Sir, who will teach?
An overview of some topics. So I have already told him that you have studied so far the chapter on metric spaces. So he will start from norm spaces, one-off spaces, etc.
Yes, sir.
So I will confirm from him once again. So he told me that he will prepare some lecture notes and he will send in advance. But so far he didn't send. But I will let you know in a couple of days about the lecture.
Sir,
Yes.
sir, can outers can join? Outers can join that session.
Outsiders, I don't know, maybe there might be some problem, but you can forward the link to the outsider so they can try to
Okay, sir.
join. So I think they
Okay,
can
sir.
join. There shouldn't be any problem. But UMT only authorize
Yes, sir.
students. I mean, they do not recognize if somebody is coming from outside. But let me
Okay, sir.
confirm from Professor D'Souza once again about the lecture. So I will let
Sir,
you
they
know
will
in
give us. Okay, sir. ठीक है.
though although I have rights that people can join from outside, but I'm not sure about students. I think there shouldn't be any problem. So is there any question, comment?
सर क्विज के बारे में थोड़ा सा बता दें, कल 10 तक हम सबमिट करवा सकते हैं?
Yes, 10 a.m.
Sir, I have
जी
done
सर?
my quiz.
Sorry?
I have done my quiz.
Oh, you have done your quiz, so you can upload right now.
सर क्विज की ड्यू डेट
Sir,
बता
I
दें
will.
काइंडली प्लीज, नेटवर्क इशू था थोड़ा सा।
Quiz की ड्यू डेट का क्या करें?
सर वो बता दें, पहले थोड़ा सा नेटवर्क प्रॉब्लम था।
Quiz की ड्यू डेट है कल, tomorrow 10 a.m.
ठीक है सर।
So I will upload one assignment. So in couple of days, maybe. So you need to solve those questions.
Okay, sir.
So if there is no question, I would like to end this meeting now. Okay then. Allah Hafiz.
Yes, sir.
Excuse me, sir.
Yes.
Yes. We have one question. We have one question in this first quiz.
Yes, only one question.
7 question.
Question number 7. I will upload
Okay.
this. I will upload the lecture slides.
Inshallah. Thank you so
Okay.
much, my dear teacher. Thank you so much.
Okay. Allah Hafiz.